The Arrhenius equation gives us the relationship between the rate constant K and the activation energy for a reaction. There are actually 3 different versions of the Arrhenius equation, and I'm going to give all of them to you in this video. The first, which is the most simple to look at, the rate constant K is equal to this constant A, which I'm going to define in a second, times E, and that's like the mathematical E, raised to the power of negative E sub A over R times T. So let's just kind of break down all the terms here. The little k is, again, the rate constant, and A is a new constant that we haven't been introduced to yet that goes by a few different names. Most commonly, it is called the frequency factor. It can also be called the pre-exponential factor because it's coming before this term with an exponent. Interestingly enough, it's not called the Arrhenius constant. E sub A is the activation energy. Remember, this is the energy that is necessary for a reaction to take place. R is the gas constant, but R is expressed in different units in this equation, which means that it is mathematically different. So R in this equation is 8.3145. The units are joules over mole Kelvin. I do want to point out that it is the same R that we've used before, 0.08206 liters atmospheres over mole Kelvin. It's just that the units, liters atmospheres, have been converted into joules using the conversion factor between these units. So the number ends up being a different number. And then last but not least here, the T, of course, is the temperature, and the temperature needs to be in units of Kelvin. Activation energy is usually given to us in units of kilojoules, so it's going to need to be converted to joules for us to be able to use it in this equation. And normally in these problems, and this type of problem, you would be given the activation energy and the temperature and the A, and you'd be asked to solve for the rate constant, or you would be given the rate constant, A, and the temperature, and asked to solve for E sub A. There are 2 other forms of the Arrhenius equation. Like I said, this one is not the most common form, even though it's the simplest to look at. Another form is the natural log of K equals the natural log of A minus E sub A over RT. So this one's a little bit easier to plug into the calculator because it doesn't have this E term with all of these exponents. And all the symbols are the same as what we've written down here. And this again would be the type of equation normally you would either be solving for K or you would be solving for E sub A. Now, there's a third version of this equation that we use if we want to be calculating how changing temperature has an effect on the rate constant. So in this equation, which is going to look kind of like this equation right here, we're going to take the natural log of rate constant 1 over rate constant 2. And that's going to be equal to E sub A over R times T1 minus T2 over T1 times T2. Notice that A is missing from this equation. It's gone. So again, this is the type of equation that you would use if you wanted to know how changing a temperature has an effect on the rate constant of the reaction. So for this, we would say that K1 and T1 would be like an initial rate constant and an initial temperature, and then K2 and T2 would be a final rate constant and a final temperature. And then the other variables are the same. This equation is derived from this equation. I'm not going to go through the derivation because I know most people don't want to see it, but I'm sure that you could find the derivation going from this one to this version in your textbook. In this type of equation right here, normally you're given 3 of these 4 variables, like you would be given 2 rate constants and 1 temperature, or 1 rate constant and 2 temperatures, and you're just asked to solve for the unknown variable.